Okay, let's roll. So I want to talk to you today about multi-material simulation. Something that I think every engineer at one point has done is go and look up a material property from a data sheet. And a lot of the time, maybe that's MATLAB, and we get to the page and we see, okay, here's my tensile strength, here's my whatever property. Let me just take it and go apply it to my model. And a lot of the times that's okay because our parts are operating at the temperatures that these properties are measured. But a lot of other times, these parts are operating at all sorts of different temperatures. And we know intuitively, if you have a piece of metal in liquid nitrogen, it behaves a lot differently when you smack it against a table than it does at room temperature. And so accounting for that, especially in applications like spacecraft, where one side of a satellite could be hundreds of degrees baking in the sun. The other side could be tens of Kelvin looking off into space. So we're going to cover how to do that in nTop, and it's actually, I think, pretty slick how this works in nTop. So to start, I took this really nice model from GrabCAD. So I have to give a shout out to Alexander Vandenberg because this model is really sweet. So go check him out on GrabCAD. So I imported this model, and what I'm going to do here is just apply a really hot temperature to one side and a cold temperature to the other, and we're going to see how that affects the material properties. So if I go through this and actually construct this FE model, you can see, so of course I've done this beforehand, and I construct this FE mesh. What I do here to start is just take the properties right off the data sheet. So I'm just going to go to MATLAB like I normally would and just copy paste these values in, and maybe that's okay, but we're going to show what the difference is if you consider temperature. So nTop, you can run all sorts of simulations in nTop. You can also build input decks for other tools like Abacus, ANSYS, whatever. So a lot of people like us just for building input decks and translating those to their existing tools. But in this case, I'm going to run a thermal simulation in nTop with a lot of heat applied to one end and a lot of cold applied to the other. So what we get here is actually a nice thermal result from this simulation. And by the way, check out these color maps. This is something new. If you're an existing nTop user, look at these. These are nice. Magma. I like magma. Magma looks pretty cool. So this is the temperature that's going across the part. And if we look at some more comprehensive data sheets of temperature dependent models, you can actually see that by considering temperature use, you can make a huge difference in your properties. So here is a plot just from a NASA handbook for aluminum 7075, and you can see along the bottom, here's temperature. Along the vertical axis, there's percentage of Young's modulus at room temperature. So at room temperature, obviously 100%. When it gets cold though, or rather when it gets hot, you can see that stiffness, it drops in half, cuts in half. So imagine your materials are only behaving half of what you thought they were. That's gonna make a big difference. And so what we do to run a more accurate simulation is import that data sheet and create a temperature dependent material card. And what's so nice about nTop is that you can actually link the results from one simulation as a field. And you can see I have this, now I have this, if you look at the HUD, this is my actual stiffness property through the part. So you can see we get that almost factor of 2 difference through the part from hot to cold side. And what we're going to do is run a new simulation with this variable modulus. And so let's show what that is. So, okay, so this is in space. there's not that many loads once you're up in space, but just for demonstration's sake, let's do maybe a free modal simulation. And you can see it wiggle at the different modes, all these different modes. And the difference I want to show is what happens when we run this with a vanilla temperature independent model versus a temperature dependent model. And by running those two side by side, you can actually compare the frequencies that you generate. And we can see the differences range from a few hertz to a few tens of hertz. So is that a big deal for your application? Kind of depends on your application requirements. In a really sensitive, precise spacecraft telescope, maybe that's a huge deal. In something else, maybe it's not that big a deal, and you can just use a normal temperature model. But with nTop, you get the option. So if you want to go deep dive and make all of your material properties temperature dependent, thickness dependent, stress dependent, any kind of dependence you want, you can link that up with our field-driven engine. So that's a pretty unique and powerful capability of nTop. In a lot of other tools, there's a lot of other simulation tools. You have to really pay a lot more to get that functionality and start doing it through scripting, user subroutines, all sorts of fancy stuff. In nTop, it's baked in to the ground framework. So I guess this is a pretty quick nTop live today, but if you found any of this interesting, please reach out to us on our website or leave a comment, and we'll get back to you on some more information. So great. So thanks very much for tuning in.